Hi, welcome to Dissolved Chemistry. Let us continue our discussion on this chemical equilibrium. In the previous video, we have discussed law of chemical equilibrium and we derived an equation for equilibrium constant. So, in the present video, we are going to discuss types of chemical equilibrium and in detail we will discuss about homogeneous equilibria. Okay, so we'll continue with that. Types of chemical equilibrium. Okay, so they are categorized into two types. One is called homogeneous equilibrium and another one is called as heterogeneous equilibria. Okay, so on what basis we are categorizing them into two classes is that if the reactants and products at equilibrium, if they are existing in single physical state or single phase, then we call it as what? Homogeneous equilibria. For example, you take H2 molecules combine with I2, both are in gaseous state, reversibly to give 2 moles of HI gas. Here all the three components of the reaction are what? Gaseous in state, so therefore it is homogeneous equilibria we call. Similarly, you take in single phase where I said, so you take CH3COOH plus C2H5 ethanol. Okay, it reversibly combines in presence of AH plus to give CH3COO C2H5 aqueous. So that is how. So the equilibrium in single phase means all are present in aqueous medium and it is going to establish an equilibrium. So therefore it is also an example of homogeneous equilibria. Then what are heterogeneous equilibria? So if the reactants and products at equilibrium, if they are existing in two physical states or phases, so then we call it as what? Two or more phases we can say. So then we call it as what? A heterogeneous equilibria. Example, you can take simple example when you decompose calcium carbonate in a closed vessel. So then you will be getting calcium oxide plus carbon dioxide gas. So here calcium oxide is solid, calcium carbonate is solid and carbon dioxide is gas. Means here in two phases or physical state, the reactants and products are existing at equilibrium. Okay. Similarly, you can take, say for example, nickel, okay, solid, combines with carbon dioxide, 4 moles of carbon monoxide gas to give tetracarbonyl nickel, okay, complex which is also gas. Okay, you can see nickel is in solid form, carbon monoxide gas, and your product is also gas. So therefore the equilibrium established between that we call it as what? Heterogeneous equilibria. Okay, next move on to in detail we will go with homogeneous equilibria, followed by that we will go in detail with heterogeneous equilibria. Okay, homogeneous equilibria. See, for example, if you take the example H2 gas combines with I2 gas, okay, to give 2 moles of HI gas. Now, if you take such equilibrium, now how to express this in terms of law of chemical equilibrium? We are going to express this in terms of law of chemical equilibrium as Kc is equal to Hi raised to the power 2 divided by product of molar concentration of hydrogen and IOD. Okay, so this is how in law of chemical equilibrium we are going to express for this equation. Now, when you see into this, all the reactants and products are gaseous. So is it possible for us to express that in terms of partial pressure? Yes, of course we can express equilibrium constant or law of chemical equilibrium in terms of a change in partial pressures or the concentration terms in terms of a partial pressure we can express. Okay, we know that the PV for an ideal gas is equal to nRT. Okay, so when PV is equal to nRT, so therefore P is equal to what you will be getting? N by V into RT. And we know that N by V, number of moles of solute per volume of the solution, concentration in terms of mole per what? Mole per cubic meter it is. Okay. So same if we express in terms of, generally for practical purpose, we are going to express that in terms of mole per dm cube. And always remember, when we express this in terms of mole per dm cube, then pressure must be expressed in terms of bar. Okay. So that we should remember. So therefore we will substitute N by V as a concentration term C into RT. Okay. Where R is gas constant and T also remains constant. Okay. So therefore both are constant. If you take, then what we can call as the pressure is directly proportional to concentration. It means pressure is equal to what you will be having, C into RT. Okay. So therefore pressure of all individual components in the given reaction, maybe product or reactant, we will express in terms of pressure as a partial pressure of that particular gas. Okay. Of hydrogen we are going to express as like this, concentration of H2, okay, into RT. Similarly, Pi2 we will express as molar concentration of I2 into RT. Similarly, PHI we are going to express in terms of HI into RT. Same you substitute here. So therefore, then we express the equation as Kp is equal to PHI, okay, raised to the power 2 divided by PH2 raised to the power 1, Pi2 raised to the power 1. Okay. So now you substitute the value of partial pressures. Okay. So then you will be getting molar concentration of HI raised to the power 2 into RT raised to the power 2 divided by molar concentration of H2 into RT into I2, molar concentration of I2 into RT. Okay. So therefore RT into RT, once again it becomes RT square. So therefore RT square get cancels. So therefore here for this reaction Kp is equal to Kc, because so these are all that what remains is that all are going to remain only concentration terms in the equation. So therefore it is going to be what we can call this as Kc. So therefore molar law of chemical equilibrium, which we express for in terms of pressure, will be always equal to in terms of a molar concentration. Kp is equal to Kc we call. Okay. And always is it going to be the situation? If it is so, then we would have not derived this one. Okay. So for example, you take formation of ammonia. Say for example N2 plus 3H2 gas to give 2NH3. Okay. So when I apply the law of chemical equilibrium in terms of Kp, okay, directly I am going to write this one. So NH3 raised to the power 2 into RT raised to the power 2 divided by, okay, we will write N2 raised to the power 1 into RT raised to the power 1 into H2 raised to the power 3 into RT raised to the power 3. Okay, directly I am writing here. So now what happens? Kp is equal to NH3 raised to the power 2 divided by N2 into S2 raised to the power 3. Okay, into RT square divided by RT raised to the power 4. Okay. So now what happens? What these terms indicate? So that is nothing but your Kc. So therefore Kp is equal to equilibrium constant in terms of pressure is equal to Kc into, if you take on to the top, what you will be getting? RT raised to the power 2 minus 4. So therefore Kp is equal to, for the formation of ammonia reversibly, Kc into RT raised to the power minus 2. So therefore, what does it indicate? Always Kp is not equal to Kc for all the reactions involving gaseous reactants and products. So therefore, we will derive in general form for the Kp, okay, and then we generalize it. Fine. So we'll see that one. Well, to get the general form of Kp equation, so we will consider, okay, a general equation. A moles of A combines to with B moles of B to give C moles of C plus D moles of D. Okay. So then we will take it as PA be the partial pressure of what? A, and that will be given as molar concentration of A into raised to the power A into RT raised to the power A. Similarly, PB is equal to partial pressure of B is equal to molar concentration of B raised to the power B into RT raised to the power B. Similarly, PC is partial pressure of C is equal to C raised to the power C into RT raised to the power C. Okay, lastly, PD, okay, corresponds to partial pressure of D corresponds to D raised to the power D into RT raised to the power D. Now let us substitute in the Kp equation. Kp is equal to, so what you will be having formula, Pc raised to the power C into Pd raised to the power D divided by Pa raised to the power A into Pb raised to the power B. So therefore, let us substitute the values. So what you will be getting? Okay, C raised to the power C into D raised to the power D into RT raised to the power C, okay, plus B. Directly I am writing here C plus D. Okay, C plus D divided by A raised to the power A into B raised to the power B into RT raised to the power A plus B. Powers I am adding, okay, same terms are there, therefore we can add the powers. So therefore, what you will be getting, if you take on to the top, so you will be having this term, okay, corresponds to your Kc. So therefore, Kp is equal to Kc into RT raised to the power C plus D minus A plus B. Okay. So this is how we are going to write. And then, so this C plus D is what? Number of moles of products, and A plus B is number of moles of reactants, sum of number of moles of reactants. So therefore, this we will replace difference in number of moles of products and number of moles of reactants. So therefore, we are going to replace that with what? That is Kp is equal to Kc into RT raised to the power Np minus Nr we will write, where Np is sum of number of moles of products minus number of moles of reactants. So therefore, that we will write as Kp is equal to Kc into RT raised to the power delta N. Okay. So this is what the formula or the relationship between Kp and Kc we can derive like this. Okay. Three conditions we will see where how the Kp is related with the Kc. Okay. So we'll see that one. Relation between Kp and Kc. Okay, so we'll see that one. See here, Kp is equal to, I will write the formula. Kp is equal to Kc into RT raised to the power delta N, and we must know delta N is equal to number of moles of products, sum of number of moles of products minus sum of number of moles of reactants. Okay, so therefore, first condition we will take when Kp is equal to Kc. Okay, so it is possible when when the delta N is equal to 0. So example is H2 gas combines with I2 gas to give 2HI gas. So this is the example where what we can see is that your change in number of moles will be equal to 0 because 2 moles of reactants are reacting to give 2 moles of the product. So therefore there is no net change in the pressure. So therefore the equilibrium will be independent of the pressure. Okay. So therefore delta N is equal to 0. So therefore Kp is equal to Kc. Both are one and the same. Okay. Similarly we will take a second point that Kp is greater than Kc. Okay. When it so happens, when delta N is positive or greater than 0, you can say. Okay. When Kp will be greater than Kc, so when delta N is greater than 0. So for example, you can take PCl5, okay, undergoes decomposition to give PCl3 gas plus Cl2 gas. So now number of Np is Nr is how much? Number of moles of reactants 1. Number of moles of products 2. So therefore Np minus Nr for this will be what? Delta N is equal to 2 minus 1. So therefore delta N is equal to 1. So therefore if we substitute, so then what we will be getting? Kp is greater than Kc with what? Kc into RT. With the term RT it is greater than. Okay. So then third one is, when would be the Kp is less than Kc? Okay. So that is possible when delta N value is what? Less than 0. Okay. Example for this is already we have discussed, that is N2 gas combines with 3 moles of H2 gas to give 2 moles of NH3 gas. So here what we will see, Nr is equal to 4 and Np is equal to 2. So therefore delta N is equal to minus 2. So therefore if I substitute then delta N value in the equation, then Kp is equal to Kc into RT raised to the power minus 2. So therefore what does it indicate? So therefore your Kp will be less than Kc with the term RT raised to the power minus 2. Okay. So I hope you have understood the derivation of Kp equation and then the relationship between Kp and Kc that we have discussed in detail. Okay. In the next upcoming video we will discuss about heterogeneous equilibria. Thank you for watching and please don't forget to subscribe our channel. Thank you.